Hello, everyone. Welcome to the first episode of RH Molten ML. Through RH Molten ML, I will introduce you to machine learning concepts at a level where you can talk the talk and, if you follow closely, walk the walk. In this episode, I'll be covering the machine learning landscape. The material draws heavily from concepts introduced in Aurelien Geron's outstanding book, Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow, 3rd edition. I'll post a link in the description. Now, let's explore the key concepts of machine learning, its applications, challenges, and approaches to testing and validating models. Let's begin with the basics. What is machine learning and why should we use it? Machine learning is enabling software to learn from data. This way, the software gets better at its task as it gains experience, that is, more data. Unlike traditional software, where we program explicit rules, machine learning allows systems to learn patterns and make decisions based on data. So why use it? Machine learning is the worst possible solution to use for many problems because it requires a lot of often human-curated data to give you meaningful answers. So why use it at all? Machine learning can help humans understand complex dynamic problems for which we don't have a known algorithm, or where the algorithms are too complex to implement manually. To make things more tangible, let's look at some practical applications of machine learning. Machine learning models are trained on medical images to identify tumors, enabling faster and more accurate diagnosis. E-commerce websites like Amazon use machine learning to recommend products based on browsing and purchase history. Machine learning helps businesses categorize customers into different groups for targeted marketing. Financial models predict future sales trends, helping businesses plan accordingly. Virtual assistants like Siri and Alexa rely on machine learning to interpret voice commands and provide relevant responses. Game developers use machine learning to create intelligent, non-playable characters that adapt to player behavior. These are just a few examples of how machine learning is revolutionizing various fields. Let's now look at how machine learning systems can be classified. The first classification is based on how they're trained. So in supervised learning, the model is trained using labeled data, where we know the correct answer. This is like teaching a child by showing them examples with the right answers. In unsupervised learning, the model learns from unlabeled data. It tries to find patterns or groupings within the data on its own. In semi-supervised learning, this is a blend of the two above methods, where a mix of labeled and unlabeled data is used. In self-supervised learning, the model generates labels from input data, enabling models to learn representations without manual labeling. There may be other ways of classifying machine learning systems. Don't blame me. Next, let's consider how machine learning systems learn. In online learning, the model learns continuously from new data as it arrives. This is useful for applications where the data is constantly changing. In batch learning, the model is trained on a large set of data in batches. Once training is complete, the model is deployed for use until the next batch of data is processed. If all the data the model is learning fits in memory, we call it in-core learning. If the model needs to process the data in small batches because it doesn't all fit in memory at once, we call that out-of-core learning. We also classify systems based on how they work. In instance-based learning systems, the model stores individual instances and makes decisions based on the closest or most relevant instances. An example of this might be housing prices. If houses with 3 bedrooms in a particular zip code cluster around a certain price, the model may come to believe all houses with 3 bedrooms in the zip code are worth about the same price. In pattern-based learning, this type of model looks for patterns or relationships in the data and generalizes to make predictions. For example, a model that looks at pictures of cancerous and non-cancerous tumors may begin to make some assumptions about what a cancerous tumor looks like. After that, it will use the pattern recognition to classify further examples. Despite its potential, machine learning comes with challenges. Here are the main ones. First, not enough data. Without sufficient data, the model cannot learn meaningful patterns. In the second case, if the data doesn't reflect the problem space, the model's predictions will be inaccurate. In the third case, poor data quality, bad data such as missing or inconsistent values leads to poor results. In the fourth case, the use of irrelevant or incorrect data can derail the learning process. And then, of course, there's the danger of underfitting and overfitting, which we'll talk about in a moment. Now let's dive into how we can test and validate machine learning models. A fundamental concept here is the use of training and test sets. The training set is used to train the model, while the test set evaluates the model's ability to generalize to unseen data. Training error measures how well the model fits the training data, while generalization error tells us how well it performs on new, unseen data. Ideally, we want both to be low. Simple models, or models based on insufficient data, may lead to underfitting, in which case the model fails to predict the training data with much accuracy. That is to say, the training error is high. Whereas models that are too complex may cause the opposite problem, wherein the model will predict the training data with very high accuracy and then fail to generalize when it sees new data. This is called overfitting and will generally mean that the generalization error is high. Once the model is trained, we can adjust its parameters to improve performance. The parameters are the inputs the model uses to make its predictions or classifications. The process of training is when the model tries to determine the relative value or weight of each parameter in generating the final output. The hyperparameters are variables that pertain to how the model itself behaves. Adjusting these is called hyperparameter tuning. For instance, we might adjust the learning rate or the number of layers in a neural network. Cross-validation, meanwhile, is a common technique of using many small validation sets. This is used to ensure the model generalizes well to new data. Another key challenge is data mismatch. We need to ensure that the data used in training matches the data used in production. This involves finding representative data and splitting it into appropriate sets for training, validation, and testing. The training set is the data you use to train the model. The model will use this data to determine the relative weight of each of the parameters used to convert input to output. The trained dev set, which is an optional data set carved out of the training data, can be used to minimize the risks. So what risks? Well, the risk of the validation and test set data being too different from the training set data. This can prevent you from coming up with a workable ML model. The validation set is used to validate which of your models performs best, say the linear model or the SVM model or whatever. And then finally, the test set is used as a sanity check before you deploy your model for use by humans. I'm going to finish up by discussing the no free lunch theorem, which is an interesting paper put out in 1996 by David Wolpert. David introduced the no free lunch theorem, which states that given no assumptions about the data, that is about whether it's linear or exponential or whatever, all models perform equally well in determining the output based on the input. This means that no single model is universally superior. The key takeaway is that we must make some assumptions about the data. We must hypothesize, test, and revise models based on the data and the problem at hand. In conclusion, machine learning is a powerful tool that can help us in some circumstances to solve complex problems across various domains. However, it comes with challenges, especially regarding data quality and model validation. As we continue to explore the ML landscape, it's important to remember that there is no one-size-fits-all solution. We need to experiment, adjust, and iterate. Thank you for your time. I'd be happy to answer any questions you may have in the comments.